Okay. I'm Dan Berg from the University of Miami, and I'm privileged to introduce a very exciting panel whose purpose is to illustrate transdisciplinary fundamental research that exhibit rigor without mortis. And I wanted to thank Dick and the NSF members who put this panel together. I also want to thank Dick for assigning 2 hours and 40 minutes for this panel before lunch. Don't panic, Dick, I'm only joking. With that, I'd like to introduce the first speaker, Dimitris Bertsimas of MIT. Dimitris?
Good morning. The purpose is to illustrate, in my case, one example where disciplines from fairly distinct disciplines addressed what I consider a significant problem of society, namely diabetes. In this case, diabetes for me is a very personal story. I lost my mother to diabetes, and all my mother's family have been hit by that disease. So I've seen, when I was growing up, close and personal, what diabetes can do to people, and also how it can be addressed. So the story, it's a short story about a PhD that started at MIT. Alison O'Hare is a student who did her PhD in this area, and she and I worked together for quite a few years. After MIT, we started a company together based on our research, and I'll tell you more about it. And the purpose is to illustrate to you a personalized, comprehensive, and dynamic system for diabetes and diet management. Diabetes is a serious disease. So this is the evolution of obesity in the United States in the last 20 years. And darker colors are more areas that are more obese in the country. You see that there's a successive progression. And this is the story over 2 decades. We came from an environment in which no state had more than 15% obesity to a state that, to an environment 20 years later that no state has less than 25%, more than double. This is data from CDC. So obesity is a serious matter. And so it's estimated today about 36, more than 1/3 of the US population are obese. And obesity typically follows diabetes. It's about type 2 diabetes, about 9% of the US population, and is expected to increase very significantly. So, quoting the previous speaker, Don from University of San Diego, he said, there are no disciplines, there are problems. I aspire to that idea. So the question is what to do to address it. So currently, if somebody's, I'm pre-diabetic myself, so, not too surprisingly, given my mother's history. So when I visited the doctor and a nutritionist and so forth, they gave me generic advice. They tell me to eat less carbohydrates, exercise more, and so forth. Hard to follow. It doesn't have enough specificity. So what we try to develop, working in a team, and I'll tell you the various disciplines that contributed to that, we tried to develop a system that learns your food preferences, your exercise preferences, learns also your metabolic situation. If I eat a banana, and if Dick Larson eats a banana, our glucose level increases in a different way and decreases in a different way. It's very different for people to people. So learning that effect and then providing suggestions for food and exercise. We don't prescribe drugs at the moment, although we are working on that, to affect the person's glucose level and diet. So the fields that contributed to that, and I'll make an illustration of the system we built so you will see. So my discipline comes from an applied mathematics, what's called operational research. Some of you might be familiar. This deals with building models, and in our case, using optimization ideas. But what we needed is somebody who has an understanding of nutrition sciences. So we collaborated with a nutritionist at MIT, the person who works in this area. an endocrinologist. I mean, you have to understand how the metabolic situation works. So not surprisingly, we work with endocrinologists. And then when we build a system, you have to really understand, you have to build a computer system. It uses databases, implements this in code, and so forth. And then perhaps on the more surprising aspect, we realized that we needed to understand aspects of economic theory. And the specific aspect of it we actually utilized is work by Kahneman and Tversky. Kahneman won the Nobel Prize for his work on how people decide. And it wasn't that one day I thought, let's write a paper on this. When I started working with actual people, I observed that people are not particularly rational in what they do. So I wanted a framework to utilize this understanding to make what we propose better accepted. So we utilized that. And finally, when we actually implemented the system, we engaged people that are training in psychology, understanding how people work. A lady, the lady from Southern California mentioned that how people decide and what they do, I have also observed it myself, are actually not often the most rational things. So understanding how people decide and also how to motivate them to adhere to suggestions is actually the biggest challenge. So therefore, we worked with cartoonists and with psychologists to observe data and then make modifications in what we propose to make what we propose better accepted. So this is a summary of the disciplines that we utilized. And it's not that we thought, let's use a discipline. It was trying to solve a problem, and the problem, in a way, guide us what it was needed to address the specific aspects of it. So this is a short demonstration, I don't have a lot of time, of a system that we built. It's called CLIA, for Lifestyle Analytics. It's a female name. You probably cannot see all the details here. I only want to give you a sense of it. But in the beginning, you say your personal characteristics, how old you are, what is your weight, and your objectives. If you have a glucose objective, a diabetes objective, you say what your objective is, and what is and if you have weight objectives. So then there are brief ideas about food, about variety, for example. Do you like high variety, low variety? And also, what is the budget that you have, a low budget, a high budget, and so forth. Again, this was illustrated from what we observed. We proposed healthy foods, but then we realized that for many people, cost is a significant matter. So therefore, we needed to adjust that. And then how much time you have to prepare meals. It could be 0. In this case, we actually have worked with a company that provides healthy foods delivered to you, or high, low, medium, 0, low, medium, high. And then various preferences on your lifestyle. So this is part of an online questionnaire. And then if you are restrictions, if you have allergies and so forth. And then we try to learn your preferences. And the way we learn your preferences is we have experimented with multiple methods. The way we have observed it works the best, if you deliver to people choices, you say, you would like A or B, and you have an enticing picture of A. It's a good thing we have lunch after that. So in which we saw the pictures, we describe them, and the user says A or B. Currently, the system says it's neither or both. And based on these answers, you generate a new question that is personalized to you. The specific methodology we use to generate a new question is actually optimization ideas, the details of which is not the time to say. But there's an underlying model guiding you which question to answer. And what we have found in a relatively few questions, it takes about 10 minutes, you actually understand people's preferences on food. Even working with a nutritionist, we have developed a database for about 700 recipes that also are affected by cultural considerations. For example, if you go to Texas, in fact, this is a real experiment, and you give a set of recipes that are more appropriate for the Northeast. They are not very popular. So we developed a Texan database. We worked with a hospital in Singapore so text and recipes in Singapore, they will throw you out of the room. So we developed Asian. So culture matters in these things, in food in particular. So we developed a collection of recipes. This is ongoing. We have now a dietitian on staff. And so therefore, in the end of the day, after 10, 15 minutes, we have an understanding of people's preferences on food. And now the real work starts. Now we have measurements. So the system, if it knows nothing about you regarding your metabolic situation, proposes certain things, proposes a meal plan. So this is a meal plan for the week. You can pre-populate it with choices that you have, they are predetermined because you have obligations. For example, today we have lunch here. I mean, so there are things that you might like to have independent of algorithms. So then using our system and our search engine, you put the foods there that you like, and then the system, LIA, optimizes the rest. It solves an optimization model, and then it has the capability that the user, if the user would like, is to put the glucose level before or after a meal. So therefore, we get partial information about your metabolic situation. We have found that after 10 or 15 measurements throughout, let's say, a period of two months, we are able to adjust very much to your needs, very personalized. So the system then optimizes, as I mentioned. It takes about 2 minutes on the cloud. It uses an optimization model of the types that we developed in my discipline. And then during this period, we have worked with a psychologist, actually, to understand. One complaint of our users was that 2 minutes is too much time. This is an online system, right? So we developed information together with our nutritionist that are useful to you, but informative. And what we have found is that actually people enjoyed it quite a bit. And the 2 minutes waiting was not wasted. In fact, they were more informed as a result. And we have found that the moment we started having more informative information, the use increased, did not decrease, even though they were waiting 2 minutes. In the end of the day, you have a plan, which you cannot see. And then if you click on a particular day, you see what you have for breakfast, what you have for lunch. There's also exercise suggestions, what you have for dinner, and then you have a prediction about your glucose situation during the day. We try to be, the model we have is such that we try to be under 180 milligrams per deciliter all day, and also the nutritional characteristics of the meal proposed. So currently, we are further working on other things. At the moment, we have about a few hundred users of the system, for which we have learned quite a bit of what people do and do not do. And we have found that with quite a few of them, we have found that it has made a difference. And we have found others who actually do not follow it. So we are trying to understand. But we know that in general, the people that follow such systems is not particularly high. In our system, it's closer to 50%. Admittedly, these are motivated people, I cannot say in general, but we have some data on that of relatively large size numbers. So what we are currently working on, and again, the multiple disciplines contribute to that, we have an iPhone application and an Android application, but in addition to that, we are currently building a system that these smart devices have GPSs, and then they know where you are. So they also know geography. They therefore can find restaurants in nearby areas, and using natural language processes, we can read the menus and propose foods that are appropriate to a diabetic. A very significant problem for those that are diabetic. You go to a restaurant, all bets are off. It's very hard to order and so forth. That's an example where you have multiple disciplines helping. There are many other features that we currently have. For example, we create a grocery list for people, and also a refrigerator list to make it. So all of these things have been developed by observing what people actually need and then finding the appropriate disciplines to help us solve the problem. I recognize I was brief, but this was just one example of my experience where multiple disciplines, at least in this case, were absolutely needed. It would have been a failure to just consider, here's an optimization model, see you. It would, you need, and I'm certain, for example, now I said cartoonist, why do we need it? Because we have observed that certain populations, whenever you have a more somewhat distant, not a human person giving advice. We have done experiments, and the people that follow these things, when sort of a cartoon character gives advice, in fact, increases. We have lots of data on that. So, so that's an example that, coming from my background, I would have never thought, to be honest. So thank you very much.
Thank you. Thank you. We'll have time for questions at the end of the session. We're going to proceed to the next speaker, Nalini Venkatasubramanian from the University of California, Irvine.
Yeah, I know it is. Just trying to get rid of
that. Good afternoon, everyone. My name is Nalini Venkatasubramanian. I'm on the faculty at the Department of Computer Science at the University of California, Irvine. I've been there for over 15, 16 years now, and prior to that, I was at HP Labs in Palo Alto. So I started out my career at HP Labs working on service-oriented architectures, those days for data services back in the 90s, and looking at e-services, web services, technologies that we've come to be familiar with today. Over the years, we've applied this notion of a service-oriented architecture and the challenges therein into many different domains, starting from, large-scale data delivery, from multimedia data delivery to mobile systems to pervasive computing. And more recently, we've looked at this concept of smart cities and how these service architectures can apply in the context of smart cities. About a decade, more than a decade ago, we started looking into the domain, a focused domain of emergency response, and looking at how information technology can improve information flow in these crisis response networks. And that sort of leads to this notion of safe and resilient cities and why they're so important. Before I move on, I would be remiss if I did not acknowledge my partners in crime over the years. Several partners, both from UC Irvine as well as several other universities. One of the things I'd like to point out is over the years, we've worked with several government agencies at different levels, starting from cities to counties to the state level to FEMA and DHS, looking at how information technologies can help in the emergency response process. And one of the things that I'd like to point out here is that this is one of those areas where really you have a merger between technologies and the human processes. And it's also not just the humans that are involved in the process, but it's also, there's a very well-set process methodologies that responders and organizations follow. And so it's not designing technology for technology's sake, but being able to improve a process, being able to understand the communities on which that process is played out. That has helped. So why are cities interesting? They've always been interesting, and more recently, I think this was I think it's a World Health Organization statistic that says in 2015, more than half the world population is in cities. We expect that to go up to about 75% by around 2050. And so you're really looking at large, huge numbers of people in very small areas of the world. And urban populations, why they get attracted there, because this is where the economies of the futures are being built, and that's why it's important for us to understand how these systems work. These communities have many different stakeholders. They involve the average citizen, the school-going kid, the senior citizen, the people who are at home. They involve governments, local, state at different levels. They involve local industry and small businesses, your mom and pop shops, all of which integrate together into a community fabric into which they are, that essentially provide those, that make those cities. Cities are made of these communities. These communities require services. These services may be the functional requirements. I need roads to go on, I need energy, I need building structures, and I need communications, water, wastewater systems. These standard built infrastructures that we have over the years been designing and building and engineering in many ways. And on top of these functional requirements, which means that I need these things to operate to be able to carry out my societal processes, I have a bunch of non-functional requirements that these stakeholders want on top of these. I need these services to be efficient. I need them to be always available and dependable, cost-effective, flexible. I decide to take the metro today. I decide to drive down tomorrow. I need to gather different kinds of information. There's sort of this transition from being something that's more infrastructure-centric to being more information-centric that we see today, this shift in paradigm. And all of these non-functional requirements are being met through this, at some level, through this transition in this paradigm. These stakeholders that you see on the left-hand side need these trade-offs to different extents at different times, which makes the problem more complex in the sense that I need different levels of security, reliability. When I'm in a fire and I need to be protected, maybe my privacy is not of the utmost importance. But if I'm being monitored as to exactly where I am every minute of the day so that the firefighter can get to me, then it is a matter of concern. So fortunately or unfortunately, there are lots of new technologies to provide us some of these new services. So the Gartner Group says that we have this new burgeoning IoT, Internet of Things ecosystem, which is going to grow to be very large, presents a whole bunch of new opportunities. Every person, every thing that you buy from Walmart, the microphone, my phone, every one of these is both a source of information that will help in this societal scale process, but it is also a destination for information that is coming to guide how users and the community plays out in these societal processes. Over the years, there have been a lot of developments in sensing and control. The cyber-physical systems community has made significant strides in these. The question is, with this new paradigm where everybody and everything is a source and destination of information, can this ecosystem in a city become sustainable? Can it be resilient, scalable, secure, private? What if I need all of the above? Do each of these systems, we have smart water systems, smart grid, smart transportation systems, intelligent services. Each of these, in some sense, are evolving, but they are evolving independently at some level. Can these systems, new systems, have new vulnerabilities and bring forth new interactions? So these are I'm going to focus on one thing, which is resilience, which I believe, given my inclination towards thinking about what happens when there's a large disaster, this is a new challenge. There's a presidential policy directive that defines the term resilience, of community resilience specifically. But I guess the key operative phrases here are we need to be able to prepare for and adapt to these changing conditions and recover rapidly from them. So preparation, indicating things can be done a priori, and adapt, meaning things have to be done on the fly as the underlying dynamic conditions change. So there's a bunch of different challenges with these cities, some of which are obvious. With this rapid growth urbanization, you have to deal with this very large scale and density of populations. It can be both an advantage and a disadvantage. If I have to send a message to everybody in this room, rather than sending individual messages, maybe it's enough if I send one to whoever is speaking on the podium. If we have to evacuate the building, for instance. So the scale and density presents both challenges and opportunities. The aging infrastructure, cities, for whatever reason, they are old, especially if you go to Europe, they're old. They have aging infrastructures. You have to deal with these infrastructures to determine whether you retrofit them to be able to meet with these new demands, or if there's a large disaster, do I rebuild? Today, there's this notion of recovering from a disaster. You talk about recovering forward, not recovering to the state that you were in. Can I bring in these new capacities now to make things better than what they were before the disaster happened? These new social structures, there's a diversity of needs. You have increasing numbers of aging populations in these cities that now need specific demands and attention, and how can technology help? How can I make sure that when there is that large earthquake and a fire that follows, that cascades from that large earthquake, all of these populations are met, both during normal times and during disaster times. If you think humans are irrational during a normal day when you have to give them, tell them to follow their diet, they can be extremely irrational when it comes to a disaster. The ability to deal with service continuity and recovery despite large and small natural man-made disasters is interesting. So in some sense, while we have pieces of technologies or pieces of science that essentially deal with addressing some of these issues, to be able to understand all of these together when these infrastructures and humans and services interact with each other and potentially interfere with each other, new design principles are needed rather than developing one-off solutions. Today we have, cybersecurity for smart grids. So what happens when there's an earthquake and the water fails and the smart grid fails, and there are implications on these different infrastructures as they interact with each other? We need ways of understanding what that really means. So I'll talk about a few design principles that we have learned over the years. I'm not going to talk a whole lot about that. I'd encourage you to ask me more during the panel discussion. One of the useful strategies we've had is, can I come up with ways of structuring the representation of these different entities, whether they be devices, whether they be events, whether they be social entities, the needs for these functional and non-functional needs for these different entities. Representation is important because representation gives you a state upon which you do adaptation. We have over the years applied this notion of an observe, analyze, adapt cycle. This applying the principles of computational reflection, which originally was applied to programming languages, but taking them into cyber-physical systems and today into socio-technical systems is an interesting challenge and an interesting opportunity, because we have methodologies to observe the evolution, create a representation of the state of that evolution. But what can I do with it to adapt, to improve the systems, their performance, their resilience is an interesting issue. These systems are by definition cross-layer. There are devices, there's geospatial events, there are humans, and we need tools. We can't create disasters to understand them. We have to have tools to explore and understand them. Over the years, I've found that formal methods-based tools are very useful, but it's an issue of how much, I was just talking to Pramod, I think, about how much rigor do you put into the process. It's interesting to have rigor, but if that rigor, for example, model checking takes 2 hours to do, I'm not going to be able to respond to these changing events in time, or sometimes it takes days, right? So the issue is, how can I come up with lightweight, rigorous methods that will allow me to respond in time to these different events? And over the years, we have done this at a campus level, where we have developed this observe, analyze loop at a campus level. We have worked with the fire practice to be able to apply this observe, analyze, adaptation loop to the fire situation awareness, and looked at where things can go wrong in this other project. And today, we're in the process of going from dependable smart spaces to resilient cities. There are a couple of projects. There's just one that I'd like to briefly mention. This was a project that we did last year. We instrumented a low-income housing facility in Montgomery County, Maryland, to help people in there with very cheap technologies. I'd like to call this democratizing Internet of Things. Technology is not just for people who have the technology wherewithal and the money to buy it. The idea is, how do I make these cheap technologies available in the masses to populations that could not possibly deal with them? And how do I make this resilient? So we built this. We had data going into the cloud, automatically going to the senior who had fallen down. But the issue is, after a couple of months, those technologies wear out. We took these cheap things off of Micro Center and built these boxes, but how do I make it resilient? How do I make it continually operational? So resilience is a very big issue, despite the fact that we have these large advances. Thank you.
Thank you, Nalini. Our next speaker is David Woods of Ohio State University.
Pop that up. No, pop it up. I just have mine. Oh, okay. So you're good here. You want to use this, correct? There you go.
All right. We all talk as if the world is orderly and neat. We all talk as if the world is orderly and neat. Reality. The system does what it was designed to do. Just leave it up, right? Except that's not what the designer intended. And that humble statement is a reminder to us that the world is more complex than we think. And we've seen this in the last couple of speakers. So let me give you a couple cases to ground the real messiness. It's a Friday night in a hospital that's becoming all digital. A nurse just received a set of medicines from the pharmacy, except those weren't the ones she had ordered for the patient. She called down to the pharmacy tech. But other nurses were already calling in significant discrepancies for their patients, too. They started to realize there was a problem hospital-wide. They called in all the available personnel in order to try to provide the correct medication to all the patients. By Saturday morning, a senior pharmacist realized he could use paper printouts of the last reliable medication administration records, and then the only machine left to communicate around the hospital was fax machines. They hadn't been removed yet. So they faxed them all over. Only later did the clinicians realize, meanwhile, right, the computer techs had lost all of the digital infrastructure and the restore from backup had failed. The outage lasted for 36 hours. By extraordinary efforts of the staff, no adverse medication events occurred. Or think about June 2nd, 2008, in an air traffic center in Dublin. A software system fails. All of a sudden, the screens for all the air traffic controllers have lost and inaccurate and inconsistent information about the planes approaching Dublin Airport and Europe from the west. The controllers, however, knew how to do things in the old way. They were a source of expertise on the old ways, and they shifted to the previous process. Unfortunately, it was a less productive process, so significant air traffic delays occurred for transatlantic and European traffic. That was a bad day. They thought they fixed it. 3 more times the same thing happened over the next month, till the new computer system was discontinued while a variety of organizational software and hardware changes were implemented and tested. Oh, you're in the ER, you're the nurse trying to get medicine for a critically ill patient from a computer-based dispensing system. You've discovered that the automated dispensing portion is now unresponsive to all inputs. A variety of physicians and other personnel come to your aid to try to figure out where can we find the needed medications. A pharmacist arrives and arranges for the staff in the pharmacy to set up runners from the floor below responding to telephone requests. The patient eventually received the requested medications, her condition improved, and she survived. That's the reality out there. These aren't one-off cases. These are the character of the universe that we're talking about. They represent only a small subset of the kinds of complications and interactions and adaptations that we just heard about, which we could talk about in urban firefighting, wildland firefighting. Our systems are more brittle than we realize, right? Failure is due to brittleness. Success comes from systems that create and sustain sources of resilience. Why don't we have more failures if our systems are so precarious? Well, look at these stories and others that we collect when we study these cycles of adaptation that were just hinted at quickly at the end there. Why not more failures? Because people are adapting at the boundaries. They are unvalued sources of resilience. They recognize that challenge happens much more often than distant perspectives realize, or planners and developers and envisioners realize. In fact, there's a law for that. It's called the fluency law. Well-adapted work hides the difficulties handled and the dilemmas resolved. So they're not seen by others, and that work to be a source of resilience and adapt at the boundaries when surprise happens. Don reminded us that surprise is inevitable, it's actually common, it's actually frequent, it's actually going on all the time. Why could those people respond? Because in all of those settings, they had a tangible experience with different kinds of surprises. They had practice, right, interacting in a variety of ways and changing their mode of operation, how they interacted with different people. Notice in all of those stories, there was a critical property that isn't in anybody's model. It's called initiative. None of those stories would have had successful outcomes without initiative on the variety of agents and roles interacting in those stories. So these illustrate briefly the critical properties of, let's use the most neutral term I can come up with out of all the alphabet jargon soup that all of us academics create. The most neutral one is the adaptive universe. We are all in it. We are subject to its basic rules. And guess what? It doesn't work the way we think. Let me repeat that. It does not work the way we think. And all of us are out there trying to model, simulate, whatever. It doesn't work the way we think. We are all in a transdisciplinary, multidisciplinary, no-disciplinary process of inquiry to figure out how this works. And we need to do it because, right, we can't hide behind the comfortable simplifications anymore. Right? So what used to be, in the sense of smart services, what used to be a special technical issue when we started, Don and I, for example, with nuclear power or cockpit automation or space missions or whatever, these were the places, high criticality, high performance worlds where we saw this. But now, we are increasingly dependent on brittle systems in all areas. Our models of how we utilize these systems and where they're brittle and how we overcome brittleness are very poorly calibrated. Our systems are much more precarious than we think. Oh, what happened last week? An unnamed 60,000 student university campus experienced the complete failure of its digital infrastructure for classes, exams, assignments, class notes, and everything. Unable to restore from backup, the outage lasted 7 days. I'll let you figure out who it was. And then guess what's coming, folks? Cyber Monday, right? So how am I doing Rigor? I'm going to one of the companies that depends on its economic viability. It's not safety like in aviation, right? Their long-term economic viability depends on their digital infrastructure performing throughout Friday through Cyber Monday. If they don't, and if there's a failure, not only will they have a bad year, they might not exist in the digital services industry. So what am I going to do for Rigor? I'm going to go hang out. I can't hang out during it this year, but I'm going to get the after-action report. Right? So these are the kinds of studies that we do. We go out and look at adaptive cycles. We go out and uncover the hidden sources that allow us to operate systems that otherwise would be too brittle to be viable in the long run and would collapse in the face of inevitable surprises. So how do we do this? We go and contrast in these studies cases of success with failure. Unfortunately, we have too much data on the failures, right? And the workarounds and kludges people go through to make the system work. What we need is more data on a success story. So we go out and try to work with companies that are successful in adapting to surprise, right? And the shape of surprise to come. And so our basic unit of inquiry is an adaptive cycle. And we got a hint of what an adaptive cycle was like. Triggering events, right? Initiate a series of adaptations across different units, right? Among the different roles, levels, and organizations. In fact, remember, it's messy. So it's better not to think of it as a system or an organization. It's really a tangled layer of sets of layers of relationships, a tangled layered network out there. And these changes often stall out, right? They create too much extra workload and demands on people. Sometimes they fluoresce, they flower, and we see things grow in a variety of ways. A simple example of a stall is a law Don Norman named called Gruden's Law. And we heard about the electronic medical record yesterday. Well, the 60-year history of failures in the electronic medical record are largely attributed to Gruden's Law. Right? Gruden's Law means that you have to think about when new technology comes in, who pays the workload costs and new workload risks and risk of new bottlenecks, and who receives the workload benefits from the new information or activities. Right? Gruden's Law means new computer systems are unlikely to be accepted or used as designed when those who pay the cost in workload do not receive benefits from the new technology for their role. Only people in other more distant roles receive the benefits. Remember, the stated gain of the current introduction of electronic medical records is explicitly, all right, to enhance billing, not enhance clinical work. Hence, we see the operation of that law. However, what we're really interested in and what we really need to be studying more is examples of fluorescence, where a change triggers a series of adaptations that open up new spaces, new niches, new capabilities that are seized on and taken advantage of by other roles and other layers in the organization. And we start to see how that cascade of adaptation plays out rapidly. We've heard a couple times over these 2 days of people referring to the contrast between these stalls that are commonplace, but also that we have fluorescence in a commonplace way too with new technology, trying to understand what produces those. it turns out a key concept, there are many key concepts that are different than what we think about normally, and we need to explain them. We need to understand them, we need better data on them, we need better models on them, and we need to be able to put those into action to produce those, to engineer systems that actually have these properties. Graceful extensibility is one. Graceful extensibility is simply an extension of our common concept of graceful degradation. In the examples I gave you, right, people adapted to make sure the system gracefully degraded. Right? When I go look after Cyber Monday, I'm going to hear a lot about mechanisms that were implemented to produce graceful degradation should problems arise to the digital infrastructure for businesses over that critical time period. Graceful extensibility goes further in a positive sense and says these things are going on all the time to make the system work, to make the system new, to make the system achieve new goals and seize new opportunities. Graceful extensibility as a form of resilience asks the question, how does the system function and change when events produce challenges at and beyond its boundaries? So I mentioned a couple of the different kinds of ideas that matter in the as we start to understand and study the adaptive universe. We can do this. It starts with critical, difficult, empirical work because it doesn't happen in a laboratory. It has to happen through partnerships that create access. Often there are multiple observer research teams that have to go out. Often the studies require months rather than a few days or a few runs in the laboratory. So let me close with apologies to Dickens. It is the most optimal of times. It is the most precarious of times. It is the age of sure wisdom. It is the age of overconfidence. It is the season of light shining from omnipresent smart services. It is the season of darkness blinkered by production pressure. It is the spring of hope from autonomous machines. It is the winter of despair of complex networks. Before us is the allure of faster, better, cheaper. Before us is the experience of sudden and inexplicable collapses. Our system of systems is almost in clockwork heaven. Our systems are fragmented, running down the other way rapidly. Not one or the other, but the signs of a single world we all live in, unfortunately, we mostly try to hide from. It's the adaptive universe, and it's time we figured out how it worked. Thank you.
Thank you, David. The last speaker of the panel is Professor Justine Cassell of the Carnegie Mellon University.
Don't forget to plug in the audio, okay?
It's always dangerous to switch computers in the middle because, as you've heard from everybody who's spoken, the world is a messy place, and it has it in for technology. So I'm really struck by the difference between the speakers on this panel and the speakers on the previous panel. The previous panel told us about innovation. The speakers told us that innovation comes from not reading, but just jumping in with both feet. They told us that you need to move into the world in order to build autonomous systems, but those autonomous systems should not be tested before they're implemented. Oh, good. That's a good start. Let's see. And I thought I was going to have to disagree with each of those statements all by myself, but the speakers before me have already done it. They've said that we need to observe data and iterate. We need to make sure that there's a merger between technology and human processes, and that people are adaptive, and so we need a kind of an adaptive cycle. And that fits in exactly with what I'm going to talk about. I'm going to start with an example of bad work. And I very rarely do this. But a student of mine sent me this paper just a couple of days ago when I was finishing up this talk. And I thought it's such a great example because it seems so cool. And it's so wrong. And here's the example. These researchers, some of whom on this paper were quite well known, and the paper was published in a good conference, decided to see what impact on rapport between the person and a virtual human on the computer screen would arise when the computer, in their words, displayed inappropriate emotions. And so they had people tell stories to the computer, And they had, in their words, the virtual humans respond by being happy, sad, or mad, opposite to what the story called for. And the way they did this was by showing a smile, a pout, or a frown. So happy, sad, mad. And to their surprise, the research showed that inappropriate emotions led to more and better stories. Any idea why? You didn't know this was going to be interactive, but I really believe in this human interface. Any idea? I'll do a demo. You try harder, that could be it. Yep. I'm going to do a demo. Can I use you for a demo? Okay. So you have to stand right there so the audience can see me. And I'd like you to tell me something about the nature of diabetes.
A deadly disease. Chronic. More?
Nope, that's good. Okay, could you see my, my facial expression? He said that diabetes is chronic and a deadly disease. That's a very serious thing. And I pouted and I frowned. I went, does that look like sad and mad to you? It doesn't. It looks like concern. It is, in fact, what we all do with the muscles between our eyebrows when we are trying to demonstrate empathy for what somebody else says. Thank you. You may sit now. So the reason this is important is that these researchers made a classic mistake in the field of embodied agents, whether those agents are virtual humans, graphical agents on a screen, or robots. They seem to have assumed that there is an intrinsic and unbreakable link between signals and underlying psychological states. But there isn't, of course. When I taught English as a college student to Japanese businessmen, I was trying to teach them emotion words, and I said, what do you do when you're happy? There was one woman in the room, and she said, I put my hand in front of my mouth. Oh, that's not the expression I expected. So there is no intrinsic link. In fact, there are inferential links. This is what the social sciences tell us, but if you don't read, you're not going to find this out. So you have to go into the world and do not armchair research, but real observation of real people, their needs, their processes, their behaviors, their desires, in a very messy world, but a world that can be predictable if you do it right. So my students and I, and this is how I've done my research for the last 24 years, we depend on looking at videotapes. We look at interactions among people, and we build models of the links between the looks on their faces, the movements of their body, and their putative underlying psychological states. We always need objective evidence of that underlying psychological state. We need ground truth, something you don't get if you sit in your armchair and say, I know sadness is a downturned mouth. And so, for example, in some research we're doing now, we use a technique that's very reliable called thin slice coding, where we have 5 to 10 annotators look at a videotape in 30-second slices, but we mix up the order, and we ask them to assess the underlying psychological state. It's highly correlated with self-report for things like rapport, interaction between people, engagement, and so forth. That's one kind of ground truth. Those models, for us, always serve as the basis for the algorithms that we build into the virtual humans or embodied conversational agents that we build. And over the last 14 years or so, we've built virtual humans for a variety of purposes, because those models are, as Stu Card says, they are theories with a purpose. They are ways of modeling to achieve a function. We know, for example, that when there is rapport between students, they learn better when they collaborate. That when students feel like they are respected by the teacher, they learn better. That actually accounts for more variance in the classroom than any other single factor. Amazing. We know that when people feel engaged, they are more honest in census interviews, and so forth and so on. And so for each of these purposes over the years, we have built virtual humans, and those virtual humans have allowed us to test our models as well as to build interfaces to large computing systems. So in each case, we begin with no technology in the room. We begin in the messy world where people interact with other people face to face with no technology between them. And we look at what they do, and we ask ourselves how what they do relates to their social intentions, and from there to their underlying states, and from there to the states and intentions and behaviors they desire to evoke from other people. So it's a full loop, but you can only get it by watching carefully. So here's an example. We ask first what interpersonal states have a positive effect on a certain kind of interpersonal dynamic. So right now we're interested in collaborative learning. We're looking at how MOOCs might do a better job, for example, in discussion fora. What is it about rapport? Can we detect rapport in a way that might increase learning? We're looking at survey interviews because with the advent of cell phones, the survey interview has tanked. Survey interviews are predicated on the fact that you call a certain number of people in every neighborhood in every town. Does your cell phone let us know what neighborhood in what town you live in? Not anymore. So survey interviews need new technologies. They're hoping virtual interviewers will do it. But what they haven't realized is that just like real interviewers, people draw inferences about the behavior of the virtual interviewer. And so it had better have a model of those inferences. Okay, so right now we're looking at rapport, which is a sense of harmony or coordination between people where you feel good about an interaction. We look at how people display rapport through their behaviors and their language. And then we look at what that language and nonverbal behavior evokes in another person. Then we transfer that to a virtual human and look at the effects. We do that using the technology called A Wizard of Oz that Maya kind of disdainfully tossed aside. And the reason we do it that way is because you don't want to build a fully autonomous system until you know that your theories are accurate. If you are interested in both theory and implementation, you must iteratively and adaptively create those technologies over and over again until they're right. But that's too expensive to do, both in time and in resources, if you fully implement first. So we bring people into the lab, or we go into classrooms, or we go into hospitals, or we go into survey interview think tanks, and we collect data. We've been having a lot of fun over the last year or so looking at 14 to 15-year-olds who are peer tutoring one another in linear equations. It's a task that they have to do at school. They're doing it with video cameras on them. And what we have found is that the number of insults that they trade predicts their learning. What a surprise. It's particularly a surprise because so many people in the field of adaptive tutoring systems have moved towards building tutors that are more polite. That's a problem, because politeness doesn't give you learning. Now, you were all teens at one time, unless you have some magic I don't know about, and I wish I had that so I could have skipped my teenage years, but I'm guessing you all went through that stage, and so you can probably remember trading barbs as a way of illustrating the depth of a friendship, as a way of illustrating that you have a special relationship with someone, and you might call that special relationship with rapport. We know that because what my students and I do is annotate the videos of children talking to one another, or of them playing, at 1/30th of a second intervals. We look at every single movement of the eye, of the head, of the torso. We look at every noun phrase and verb phrase. We look at the pragmatics of the utterances, whether they are statements and questions, and we assemble all of that into conversational strategies, and then we look at the impact of those conversational strategies. We apply machine learning algorithms that, rather than simply going from bottom to top, from a bunch of data to an algorithm for a system, intervene with a set of theoretical assumptions, conversational strategies here, that allow us to know what it is we're seeing. and how to build it into a system. For rapport, we currently have two models, a model of building rapport and a model of maintaining rapport. And I'm going to show you the shortest of examples here. What we've discovered is that for all of us, rapport relies in part on disclosing something about ourselves to somebody else. But for the most part, those disclosures are negative self-disclosures. So for peer tutoring, one child says, oh, now we're working with negative numbers. And the other child says, ah, ugh. And the first kid hears that and says, I suck at negative numbers, which she doesn't. And P2 says, the other child says, it's okay, so do I. What they've just done there is invent a situation where they are equally bad. Our favorite example of this in our corpus is one child who says, I love animals, but I keep killing them. And the other kid says, yeah, me too. And we don't know if that's true, but we know that negative self-disclosure is true and necessary. So we build new kinds of architectures for dialogue systems, for robots, for virtual humans to allow us to do this. And we use Wizard of Oz technologies where you don't fully implement the system, but you have a wizard follow your model in order to assess the goodness of fit. And then we build an implementation. I no longer call these autonomous implementations because just like people, they are deeply interdependent. Thank you.
Thank you, Justine. We do have time for a few questions directed to anybody in the panel. Go ahead. You have a microphone, please. It's coming. Coming right behind you.
I'd like to direct this to Dave Woods. I think I used to like Gruden's law, but I now think that it's kind of the Taylorism of collaboration. So, you know, instead of asking who does the work and who gets the benefit, and assuming that that has to be a zero sum, why not ask who does the work and thereby gets the benefit? I mean, I'm not saying every example will be easily amenable to that, but that's designing a service co-production. And those are the ones where the benefit, the total benefit produced, will vastly exceed the cost.
Correct. Correct. But I was actually going even further. I was trying to use that we have laws and they may get overturned, refined, whatever. We can understand operations at this level and interactions and interdependencies. You're exactly right, and I think we can go further because you start to see that adaptation grow across the network. And I think that's also what you're implying too, so that we see this amplification. Now, that amplification will stall eventually, and also it will happen in surprising ways. So in one study we did was of electronic ICUs, and electronic ICUs were fabulous when we studied them. It had a lot of benefits for the patient, for the rural ICU or the small hospital that didn't have as much expertise or in their staff, even though they were all minimally qualified. What it actually relied on was we had a pool of expertise of nurses who were experienced who no longer could physically handle or for other reasons wanted to handle the daily shift work of an ICU and the stresses of that. So they were happy to work in the electronic ICU supporting the less experienced personnel other places. It looked great for everybody. You know what we started to anticipate was the ways that other people in the hospital would start to adapt to make use of the electronic ICU. And in the 18 months, we observed the startup of a couple electronic ICUs, an 18-month study, right, working with 2 electronic ICUs over that 18 months, just to understand the scale of the study. What we found was people in other parts of the hospital wanted to take advantage of the electronic ICU, and I guess you can guess what they wanted to take advantage of it for: increased billable events. And I'm not saying that's good or bad, saying that's the reality. People will adapt to make use of the capacities you create.
Is there another question or comment in the back of the room?
I had a comment on that same thing. The same kind of phenomena can be observed in computer-aided dispatch centers where you have responders trying to gain awareness of what is going on sitting in an emergency operations center or at a dispatch center. And today, because you have the ability to get information from people through mobile crowd sensing type technologies, if there was a way to structure that information back to provide a better picture, a better dashboard to the dispatch center operator, then I think that certainly can go back to, it's not necessarily the provider of the information does benefit, but in some sort of an indirect way.
And it's also the reason, and we have a subtext here that we can design for these smart systems. And when you take the adaptive perspective and the slide I had up at the beginning, it's a reminder that we need to be humble as designers. Because things that will start, things that will have an impact, and it may be the impact we intended, but it may not and even probably won't stay there. And hopefully it'll be the fluorescence kind of thing where a bunch of things that we all look at as desirable start to play out. But we'll quickly start to see conflicts because human interests, right, span multiple goals, and those goals trade off and conflict. And we'll see those trade-offs and conflicts as our designs start to trigger new layers of adaptation from the different stakeholders.
Question in the back.
So your statement that the number of insults predicts performance, as a guy who graduated from United States Air Force Academy, I find this fascinating. Is there a chance these are hyper-performing students in some way?
Oh, no. There's no chance of that.
I love it. I'm going to try to bring this into some of my undergraduate classes.
So we have a couple of papers on this, but if you ask your undergraduates, they'll know that they, first of all, they'll know how much they insult one another. And second of all, they'll know that in some sense, if you probe them, that insulting mitigates power differentials. If you can insult somebody else, then they are no longer the tutor above you. You've brought them down to your size, and perhaps that allows you to learn from them.
Thank you. A question over there, please.
Oh, my name is Justine, and I'm from Temple University. I wanted to, Dave and I are on the same team, so we have some opportunity to continue the discussion. So I really applaud that you mentioned all the disasters, that, and also modeling, so that we already had discussion earlier. But I don't know how many people are programming in this room. After modeling, there's a task called programming. And we program by rules. And the designers came up with paradigms that we follow. So what I'm saying is that in the design of the paradigm, the assumptions being made in the paradigms are overly optimistic. Just like you're saying that we assume the data will never get lost. And the process is always running. And the power is always up. And the communication cost is zero. And the topology never changes. So all these assumptions made our system brittle, as you just said it. And how do you, it's a miracle that disasters don't happen tomorrow. Okay, so we're just being lucky. So the paradigm is at the fault. So I really applaud this panel, is that bringing all the, see, I think that the mission brings service into this discussion is bring everybody's feet into fire. So the modelers, the programmers, and the model builders, and the paradigm creators, and have to think twice. And what are the assumptions? Let's make assumptions explicit. And then the rest will become easier. If we hide them, we're not doing ourselves any good. Thank you.
So his comments highlight to us some of the things we've been discussing across the formal presentations in the hallways and in our groups, that there's new kinds of questions and that we should think bigger about the question we're posing. Brittleness is one example. Right? We are not making, when I first made a big deal of this for NASA and some others after some accidents in 2000 and unfortunately again in 2003, I thought by now we would have made much better progress at assessing brittleness of actual working systems and organizations. And we've gone very, very slowly. And it's almost as if we go, that's too hard, let's run onto something more tractable and get some more papers out and better probability of funding.
Exactly. So I'll give you an example of a database. Everybody teaches database, right? So everybody knows once the database schema is done, changing the schema is difficult. Now the business changes all the time. And how can we rely on this kind of technology to build a service system and you expect to adapt? It's not going to adapt.
Okay.
Okay, it's hard.
Okay.
Right?
So why don't you continue after the session?
Thank you.
Dr. Wood. Are there any other questions?
I have one.
Please.
So I very much appreciated the discussion. I'm wondering how you've been able to reconcile the differences in what's considered to be research rigor between the social sciences and engineering.
Well, that's the question. So we talk a lot about this in my lab and in my department, which is Human-Computer Interaction Institute at Carnegie Mellon, where some of our faculty members are computer scientists, some are psychologists, some are designers, some fit into neither of those three bins. It's a discussion that I think we have to have with all of our graduate students, because they are no longer going into a world where the world is divided the same way at the seams. Disciplines are historical accidents. They are ways that fields grew up, and they're ways to keep out as well as to let in. But those boundaries are no longer in the same places, nor can we afford any longer to keep those boundaries in place. So for the moment, I think we're in this liminal space in between disciplinarity and no disciplines, like Don called it, as Don called it. What I teach my students is how to make an argument for a social science audience and for an engineering or computer science audience, because I think that makes them stronger. It's like being bilingual. You know, new results are showing that people who are bilingual are better able to do algebra and other kinds of tasks, and I think it's the same thing with being bidisciplinarian.
Yeah, I also think actually some of that comes from putting students out into the field. So over the years, I've placed students in the City of LA Emergency Preparedness Department in Montgomery County, Maryland, in their CIO's office, trying to actually work with people who are actually using your technologies to figure out, what are the design criteria that will work in practice. So I think bringing that back into some sort of a technological, there are tools that as computer scientists, as engineers, we have. The question is, how do you populate those tools with realistic assumptions and meaningful assumptions that can be applied in practice? So, I think one might structure them as policies. I remember someone saying policies can have their downsides, but they can also be ways of structuring those observations into adaptation strategies, potential adaptation strategies. And I think if we start with the assumption that the underlying base infrastructure, whether it's humans or engineering structures, is prone to change, being able to observe that change and designing systems that can add new mechanisms. The extensibility that you were talking about, being able to design systems that are extensible, tells us that we're not locked into one thing. The database schema is a good example. You design a system and that's the only thing you can represent in your system. That's not the way to design. We have to be thinking about these systems because they're subject to so much change.
I refuse. Seriously, like Don, I've grown up around the boundaries and borders and in between and back and forth these different camps, and there's no difference in terms of the fundamentals. Good work is good work, and it always starts with the phenomena. It always starts with what Bacon said, right, in 1620. A collection of observations, extensive in its diversity, right? Almost a quote. I can't quite remember in my old age here. But it starts with observation. It starts with innovation and method. When you look at all the cool things we've heard about, right, you see innovation in the methods. It doesn't matter whether somebody's had social science or engineering. What's our problem? Our problem is putting tractability too early in the exploration and discovery process. Our problem is putting verification ahead of discovery. Our problem is ignoring that discovery can be studied and facilitated and pretending it's only a process of verification and specification and precision. We don't value, we don't fund. If we propose a discovery methodology, we don't get funded. So what do? So what? I go off and find some other funding and I find a way to make it happen. That's the way we get work done. And if you ask most of the people about where their most important findings or results or inventions come from, I'd be very curious to find out what percentage came directly from an explicitly funded project where that goal was what they discovered, found, invented was the explicit goal of the project. My bet if we did that study is we'd find a relatively small percentage were explicit targets, and most were serendipitous or some kind of combination, exploration, adaptation, emergent phenomena.
Okay. I think it's now time to adjourn the panel. I suggest we adjourn with a rising vote of thanks to the presentation. Thank you.
My version.
Thank you, panel. We've heard so many interesting ideas today. I don't know about you, but I'm on sensory overload with all these ideas and trying to figure out how to put them all together in some coherent package. I would just like to reflect on a little one theme here is that interdisciplinary and transdisciplinary is not necessarily new. If you look at in 1940, when operations research was born in the United States in order to help the war effort, Philip M. Morse, MIT physicist, sent down to the Pentagon to put together teams. And one of the first tasks here was anti-submarine warfare because the German subs were sinking many of our ships going over to England. And so what did they put together? They put together teams of physicists, mathematicians, engineers, psychologists, and people who were expert, let's say, on human vision. And did they go to the blackboard and prove theorems? No, they went out in battleships. They went out in destroyers, they flew in airplanes, and they understood exactly what the human process was about searching the ocean for these submarines. And as a result, they created a system which then turned the tide of the North Atlantic. No pun intended on that. But Bernard Koopman, who invented the mathematics part of this, which included some of the psychology, some of the vision work, his work was so important to the United States that it was classified as top secret for 15 years and was not published in the journal Operations Research until the late 1950s. So I just wanted to point out that little historical thing that interdisciplinary team research goes back at least that far, and I'm sure a lot farther. Now with that, lunch is served, and this is a working lunch, so remember what team you were on. I think I was on team 4, the teams, and so we have tables set up in the 2 breakout rooms, so you can bring your lunch there and work with your team. Or those who are in here, I guess you use these tables and arrange them in some way so you can eat and talk and do the teamwork at the same time. And the culmination, the final act here of these 2 days, very exciting, is at 3 o'clock. We're going to have each of the teams report. It'll be about 5 minutes each, and we'll have time for 1 or 2 questions. And that will be the summary of our workshop. So enjoy your lunch. Thank you.